2.1, the derivative function. So the derivative at a point. So in chapter 1 or unit 1, what we did is we explored limits in this form here. Okay, we had some number a and we subbed it right in. So say 2, 3, -8, whatever it was. And we found the limit as h approaches 0 of f at that number plus h. And again, h is arbitrarily small, and that's why we're saying it approaches 0, minus f at a all over h, and h being the difference between the x's. Okay, so this is like the slope formula, but as our gap between a and a plus h becomes smaller and smaller and smaller. Okay, so this equation has two interpretations. So we can either interpret this equation as the slope of the tangent to the graph of y equals f at x at the point a comma f at a. So a comma like some y value. Remember, that's y value. Or like the other interpretation is the instantaneous rate of change of the function y equals f at x with respect to x at x equals a. Okay, now we'll give you this equation in a concise notation. So the derivative of f at a number a is given by this. So this right here is not an inverse, it's not an exponent. This denotes, this is the notation for the derivative of f at the number a. Okay, and then the exact same formula. So up until now, we've only been writing it from here over, like the limit as h approaches 0. Now we're actually going to write it as f prime at a. And that, I want to say comma, we call that prime. Okay, and that's provided the limit exists. So example 1, we are going to do just like we did in we are going to determine the derivative of f at x equals x squared at x equals -3. Okay, so what we saw in unit 1 was, now we're going to go, actually, I'm just going to do this straight unit 1. Okay, the limit as h approaches 0 of f at a plus h minus f at a all over h. Okay, and our first two steps were sub in f at -3 and see what that equals, and we get 9. And our second step was sub in f at -3 plus h, and when we do that, we have -3 plus h squared. So if you think about -3 plus h, and then -3 plus h, and then foiling this, we actually end up getting 9 minus 6h plus h squared. So now we can come back to, this would be step 3. We're going to find the limit as h approaches 0 of 9 minus h squared, 6h minus plus h squared. Okay, and then we're going to go minus this 9 value all over h. Okay, so if we have 9 minus 9, those cancel out. And then from what's left, we're going to factor out the h in the numerator. So the limit as h approaches 0, factor out the h, we're left with -6 plus h over h. Now, those h's cancel out, and we're left with the limit as h approaches 0 of -6 plus h. At this point, we sub in the 0. You know what? Let me write equal signs all the way down. When we sub in the 0, we drop the limit, and we get -6. Okay, so that is the approach that we saw in Unit 1. The difference in the approach that we saw in Unit 1 and what we're going to do today is we're going to do the general form for the derivative. So we're no longer going to have this x value or the, for example, the a value that we're going to sub directly in. We're going to find the general form for the derivative of an entire function, not just the function at a single point. So an alternative way of writing the derivative of f at the number a is f prime at a equals. So the limit as x approaches a of f at x minus f at a all over x minus a. We use this general form when we want to know the derivative for a number of values of x. Okay, a number of values, that means like more than one. Okay, more than one. So repeating the process for each value is tedious. So instead, what we do is we find the general derivative of like the entire function f at x at an arbitrary value of x, and then what we do is sub in particular x values. So that's what we're going to see here. So example 2a, determine the derivative of f at x equals x squared at an arbitrary value this time of x. So this is what it's going to look like. So we're going to have f prime at, let's just go x because it's general. Okay, we're still going to do the limit. So as h approaches 0 of, we're going to go f at x plus h minus f at x. And this is all going to be over h. So the difference between unit 1 and now 2.1 is we are no longer subbing in that a value. We're leaving it as the general form for x. Okay, so if we have the function x squared, we are still going to do x plus h all squared minus f at x, which is x squared again, all over h. Okay, so the limit as h approaches 0, what we're going to do is the x plus h, we are going to expand that as x plus h times x plus h. And in the next line, we're going to FOIL it. Okay, minus x squared all over h. So when we FOIL this, we get x squared plus 2xh plus h squared. And then we bring down the minus x squared all over h. So the limit as h approaches 0. So if we were to cancel anything out, we have the x squared, the negative x squared. And then we're left with 2xh plus h squared. So what I'm going to do is factor out the h in the numerator. We're left with 2x plus h all over h. Now the h's cancel, and we're left with 2x plus h. I'll write this so we can see it very neatly. Okay. At this point, we sub in the 0, we drop the limit, and we get 2x. So the derivative of f at x, so f prime at x equals 2x. That is the general form for the entire quadratic function. So for b, it asks us, determine the slopes of the tangents to the parabola y equals x squared at these 3 points. So following the f at a formula, where we actually sub in the a, would be very tedious to do for 3 different points. So what we actually did is we found f prime at x, and we found this to be 2x. Now what we can do is we can say, okay, well, what's f prime at -2? And then sub in the -2. Well, f prime at -2 is -4. Okay, we can say, what's f prime at 0? Well, 2 times 0 is 0. And then we can say, what's f prime at 1? We can say 2 times 1 is just 2. So what we can do here is we can take the general form for the derivative and find derivatives along that entire, remember it's a parabola, right? So the slopes are going to be different. If we look at tangent lines, they're going to have different slopes all the way around, right? So the formula for all these slopes, f prime at x equals 2x, that represents all of these like blue tangent lines, and then you can go ahead and narrow it in. Okay, well, what happens at -2? What happens at 0? What happens at 1? Okay, so less tedious. Okay, investigation. We're going to determine the derivatives of these equations. So we already did x squared, so let's take a look at x cubed and then x to the 4. So I'm actually going to break this down into the 3 parts. So part 1 is just f at x, which is x cubed. Okay. Part 2 is going to be f at x plus h, which is going to be x plus h cubed. So if you remember from grade 11 university bound class, if you remember Pascal's triangle, these are going to be the coefficients of our expansion of x plus h cubed. So as a recall, we're going to have the coefficient 1, then we're going to have x cubed. Then we're going to have h to the 0. Then we're going to have coefficient 3. And what we do is we take the first number here, which is x, and the second number, and what we're doing to the exponents is, so it was x cubed, now it's x squared. So the exponents on the x's, the next one will be x to the 1, the next one will be x to the 0. The exponent on the x's go down. Now the exponent on the h's go up. 0, h to the 1, h to the 2, and then h to the 3. And the coefficients are going to be 1, 3, 3, 1. So 1, 3, 3, 1. I'll put that back on the page. So if we were to come down here and simplify this, so h to the 0 is just 1, so it's like multiplied by 1. So our first term is just x cubed. Our second term is 3x squared h. Our third term is 3x h squared. And our fourth term, 1, and then x to the 0. Anything to the 0 is 1, so 1 times h cubed. So this is the expansion of x plus h cubed. So now let's actually sub into the equation. So we're going to have f prime at x equals the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, and we've already done these 2 parts. So let's write in the limit as h approaches 0. Let's write in f at x plus h, which is our x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, we're just taking that and we're copying it. We already did all the work. Minus f at x, which is x cubed, and that's all over h. Okay, so we write limit as h approaches 0. So what can we cancel out in this line? We can cancel out the x cubed minus x cubed. So those go away. And we're left with this trinomial here. So in this line, let's go ahead and factor out an h. So if we factored out this h, we're left with 3x squared. If we factor out one of these h's, we're left with 3xh. And we factor out one of these h's here, we're left with h squared. Okay, all over h. So let's cancel out the h's, and we got the limit as h approaches 0 of 3x squared plus 3xh plus h squared. So now, if we sub in this h equals 0, we sub it into this term and this term. these two terms are going to go to 0. Anything times 0 is going to give us 0. So we are left with 3x squared. So the derivative f prime at x equals 3x squared. So the derivative of x cubed is 3x squared. Now, we're going to determine the derivative of y equals x to the exponent 4. So step 1, if we do it the old way, we'd have f at x equals x to the 4. Nothing would change. We're not subbing anything in. Now, step 2 is f at x plus h. So we're actually looking at the expansion x plus h to the exponent 4. Okay, you could write out x plus h 4 times and expand it by like the foiling method, but it's going to be very tedious. I'm going to again use Pascal's triangle. Okay, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So just a couple reviews from Pascal's triangle. If we have exponent 4, we're actually going to have 5 numbers in the expansion. Okay, so these 5 numbers are going to have coefficients 1, 4, 6, I want more room, 4, 1. Those are the coefficients. Now let's pattern the x's. We're going to have x to the 4, x to the 3, x to the 2, x to the 1, x to the 0. Now let's pattern the h's. H to the 0, h to the 1, h to the 2, h to the 3, h to the 4. So the exponents on this first number, x, go down. And they count down, they start at whatever the exponent is, which is 4, and they go to 0. The exponent on the h, so like that second term in the binomial, start at 0, and they go up to whatever that exponent is. Okay. And now we can simplify. So 1 doesn't matter, h to the 0 doesn't matter, right? Because it just goes to 1. We're left with x to the 4. Okay, the coefficients, we have no other normal numbers in here to multiply by the 4. So the 4 is going to come down, x cubed h1, x cubed h1. Now 6x squared h squared, that's already simplified. We can't do anything to that. 4x h cubed, 4x h cubed. And then the 1 goes away, the x to the 0 goes away, and we have h to the 4. So this entire this entire expression, I should say, is the expansion of x plus h to the exponent 4. And now what we're going to do is we're going to find the derivative. So f prime at x equals the limit as x approaches 0 of f at x plus h minus f at x all over h. Now let's sub in. The limit as x approaches h, we want to sub in this full expansion, x to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4 all over h. Oh, I'm sorry, minus f at x. Don't forget that. So minus x to the 4. Okay. So we have x to the 4, negative x to the 4. So we're going to have the limit as h approaches 0. And we know that all of these terms are different because if any of these were like terms, we would have collected them in the original expansion. So we know that all of these terms are different. So let's go ahead and factor out an h. We're left with 4x to the 3, right? And that one goes away. We have 6x squared h. And that one goes down to 2, 4x h squared. And that one goes down to 3x h cubed. Okay, all over h. We can go ahead and cancel out the h's. And then when we substitute this h equals 0 in this term goes away, this term goes away, and this term goes away, because all of those terms would be then multiplied by 0, and we get that the f prime at x equals 4x cubed. The definition of the derivative function. So the derivative of f at x with respect to x is the function f prime at x, where f prime at a equals the limit as h approaches 0 of f at x plus h minus f at x all over h. This is what we've been using, provided that the limit exists. So very similar to the one above, we're now calling this the definition of the derivative function. So let's use this definition of the derivative function for example 3. Determine the derivative of f prime at t of the function f at t equals root t, such that t is greater than or equal to 0. Okay, I do want to review this. Root t would be like this. Okay, so the domain on that is t is greater than or equal to 0, right? All of these numbers. Okay, so let's determine the derivative of this function. And if you notice, we did the derivative of x squared, x cubed, x to the 4. Now we're doing root t. None of these functions actually have transformations on them. We're just finding the derivatives of the original functions that we usually work with. Okay, so let's go f prime at a, or x. I'm going to write x because we're doing the general form. It's going to be the limit as h approaches 0 of f at, I'm just going to write this out, x plus h minus f at x all over h. So if you wanted to do this with the 3 steps, okay, step 1 would be f at x, it's not x, it's f at t, is root t. This should be a t, this should be a t, this should be a t. Okay, we're using the variable t. Okay, step 2 is going to be f at t plus h. So that's just going to be root t plus h. We cannot simplify this anymore. So we're done. Let's plug it in. Step 3, the limit as h approaches 0. We get root t plus h minus root t all over h. So as soon as we see roots or radicals and we want them off, we multiply by the conjugate. So we're going to have t plus h plus, root t plus h plus root t all over root t plus h plus root t. As a reminder, this term right here is just like multiplying by 1. Okay, we're not actually changing our number, we're just making it look different. Okay, so the limit as h approaches 0, let's expand the numerator. If we have root t plus h times root t plus h, the roots are going to go away. We just get t plus h. Because this is a difference of squares, the middle 2 terms are going to cancel out. I'm no longer doing that. Okay, you can expand it. I'm not going to expand it. I know they cancel out. So we're going to have negative root t times positive root t. We're going to have negative t. Again, if we have the same number underneath the radical sign, that radical goes away and we just take that number. Okay, and this is all over h bracket. Okay, you don't have to expand this. We're going to have t plus h plus root t. Oops. Okay, at this point, we have t minus t in the numerator. And when those are gone, we have an h, and this h is already factored out because we didn't expand this, right? You don't want to expand that. You want to keep it factored. These h's cancel out. And don't forget, the h in the numerator and the h in the denominator do not cancel to 0, they cancel to 1. So now what we're going to get is the limit as h approaches 0 of 1 over root t plus h plus root t. And at this point, we can go ahead and sub in this 0, and we get 1 over root t plus root t, and I get 1 over 2 root t. And that is the general derivative of root t. Okay, and this is for t is greater than or equal to 0. We can't actually have 0 in the denominator, so greater than 0. Okay, don't forget there, whenever we finish with a rational, there's always going to be a restriction here. Okay, 2 root t cannot equal 0. So divide by 2, root t cannot equal 0. Square both sides, t cannot equal 0. Okay, so the overlap of t cannot equal 0 and the original domain is going to be t is greater than 0. So note, the domain of f at x equals root t is greater than or equal to 0. Okay, but the domain of its derivative, which is f prime at t equals 1 over 2 root t, is actually t is greater than 0. It's a little bit different. That's okay. But we can see that a function does not need to have a derivative throughout its entire domain. Okay, and we're going to get a little bit more to that. So this function does not have a derivative at t equals 0. So there is no derivative. Okay, we're going to get to that in 2 more questions, but ultimately, when we take a look at the root function root t, because we're talking about at 0, there's this end point, we're going to learn that there's no derivative at an end point. So I'm going to review the standard form of a linear equation. Okay, so 1, express the form in the order ax plus by plus c equals 0. Okay, this is standard form of a linear equation. What we have to do when we express it, the equation of, for example, y equals mx plus b, okay, because we know that we're going to have a number in there for m, a number in there for b. We have to rearrange it, bring everything over to one side, and equate it to 0. And of course, if you bring everything over to one side, what is left on this side? Nothing, right? So when we're talking about the word nothing, we're talking about 0. That's the equivalent in number. We have to ensure in standard form that the leading coefficient here, so the coefficient of the x value, is a positive integer. Okay? If not, we multiply everything by -1. Okay? And we have to make sure that all coefficients are integer values. Okay? So in brackets, you can put like not decimals or fractions. So example 4, determine an equation of the tangent. Okay, so equation of the tangent, remember a tangent is a line, so we're just talking about an equation of a line, okay, which is usually y equals mx plus b, okay, to the graph of f at t equals 1 over t at the point where x equals 2. And then what we're going to do is we're going to express in standard form. So right now, we're going to leave out the x equals 2. We're going to do the general form that we've been doing for this lesson. Okay, so we're going to have f prime at x equals, the equation is the limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, so we're going to have the limit as h approaches 0. And if you want to do the 3 steps, you can. to the side of my paper, I'm going to go way over here. Okay, if we have f at x plus h, we're going to have, that'll be step 2. We'll do f at x first, which is, it's going to be f at t. It's going to be 1 over t, right? That's the original. And then if we have f at t plus h, we're going to have 1 over t plus h. Okay, we can't simplify either of these. So let's go ahead over here. I am going to change these to t's just for proper form. And then I'm going to go ahead and sub in. So f at t plus h, I get 1 over t plus h minus f at t, I get 1 over t. And then the entire binomial here over h. So what we want to do is we want to find a common denominator between t plus h and t. So what I'm going to do is I'm going to bracket this t plus h as a binomial, okay, because we have to keep it together. We can't just add like a plus h over here, okay? So the 1 over t plus h, we're actually going to multiply by t over t, right, which is the denominator of the second term. And the 1 over t, we are going to multiply by t plus h over t plus h. Again, the denominator of the first term. Now, let's go ahead and rewrite this. The limit as h approaches 0, for the first term, I'm going to get t in the numerator, and I'm not going to expand this. I'm just going to put t bracket t plus h. Okay, I am going to, because I know that these two denominators are going to be the same, I am going to expand or like make this division or this fraction symbol a little bit longer, and I'm going to put this entire numerator over t bracket t plus h. So I already have t, and then we're going to have minus 1 times t plus h, so in brackets t plus h. And it's important that you put this in brackets because in the next step, we are going to distribute that negative sign into the bracket. Okay, and instead of putting it as divided by h with the fraction symbol as our division symbol, I am going to put divided by h beside, because then in the next line, what's going to happen is I'm going to multiply by 1 over h. And it's easier to cancel out. Okay, just remember we can't divide by a fraction, or we can't divide a fraction by a number. We have to multiply by the reciprocal. So the limit as h approaches 0, for the numerator, I get t minus h, or t minus h, all over t plus h, times 1 over h. So now I'm going to take a look at what I can cancel out. So t minus t cancels out, and then I have negative h over t plus h. This h in the numerator and the h in the denominator cancel out, right? The times 1 over h. That's our goal, to cancel this out. This is our goal. Okay, so now what we have left is, and I'll write it one more time, the limit as h approaches 0, negative 1 is in the numerator, okay? You can't forget about that negative sign because it was negative h, and then over t plus h. Okay, at this point, we're going to sub in the 0, and we no longer have to write the limit. Okay, so we're going to get negative 1 over, it's t times, well, t plus 0. I'll write it all out this time. And then we get negative 1 over t squared. And I'll box that answer. Okay, so the derivative of f at t equals 1 over t is f prime at t equals negative 1 over t squared. So going back up here, I'm going to just box this kind of in the corner because it's like side work. Okay, the original question asks us, determine the equation of the tangent of f at t to the point where x equals 2. Okay, so we're able to say, okay, so I'm going to change color here. we're able to say, okay, so f prime at t is going to equal, this needs to say t. Okay, f prime at t equals -1 over t squared, right? Going back down here. So what we're going to do is we're going to find the slope, which is like the derivative at f prime at 2. So -1 over 2 squared. The derivative is going to be -1 over 4. That's going to be the derivative, aka the slope at t equals 2. Derivative / slope, instantaneous rate of change. All of these are interchangeable at t equals 2. So since we have that, what I'm going to do is I'm going to find the actual point. Okay, so I don't know where the point. Okay, so let's find the point. I don't know where the point where at t equals 2 actually lands. We know that it's going to be 2 comma something, but we don't know that y value. So from the original, we're going to go f of 2 equals 1 over, and the original was 1 over t. So now the original is going to be 1 over 2. So the point that we're working with is 2 comma 1 over 2. That is going to be our x and y value, or our t and f at t value, I should put. Okay, now what we want to do is we want to actually find the equation of a tangent line. So I'll start that here. So originally we're going to have y equals mx plus b. It's the easiest way to do it. So the y is going to be 1 over 2 equals, the slope is -1 over 4. Okay, x is going to be 2, and then plus b. Okay, 1/2 equals, this is going to be -2 over 4, which is -1 over 2, plus b. I'm going to bring this over to the other side. I get 1/2 plus 1/2 equals b, and I get 1 equals b. So the equation of our line is going to be y equals -1 over 4 x plus 1. Then the question asks us to express the equation of our line in standard form. So what I'm going to do is I'm going to bring everything over to one side. So when I look at this, I see -1 over 4x. I see a negative on the x. We know that the x value has to be positive. So I'm just going to kind of cheat and bring that over here. Okay, so I get 1 over 4x plus y minus 1 equals 0. Okay, so we've already satisfied the first two points here, expressed it in this form, okay, and then the coefficient of x has to be a positive integer. Now for like the third requirement of standard form, we have to express all of these coefficients as integers. So we cannot express this with a denominator 4. What we're going to do is we are going to multiply every single term by 4 on both sides. It's not going to affect the 0. So 4 times 1/4 is just going to be 1. So that goes to x. 4 times y is going to be 4y. 4 times -1 is going to be -4, and then equals 0. So our equation is x plus 4y minus 4 equals 0. That is the equation of the tangent line at -2. So let's take a look at the graphs. So you don't want to put 1 over t in here. It doesn't pick it up. You want to do 1 over x. Okay? And then I'm going to graph x plus 4y minus 4 equals 0. Oh, it does plot it. Okay, so if we actually take a look at this right here, this blue line, the y values are going to go from -1 to 1. Okay, that's good. Okay, so the red is our original 1 over x, right, which is our original reciprocal function. Okay, and this blue line here is the tangent line at t equals 2, or in this case, x equals 2. Decimals only picks up x. So we can see this line of tangency. Okay, and then obviously they intersect only at a single point. It's 2, 1/2. Okay, the normal to a graph of f at point P is the line that's perpendicular to the tangent at P. Okay, so we're going to talk about normals right now, but we're really going to get into that when we get into our vectors component of this course. Okay, but what we want to do is we want to focus on perpendicular. Okay, so as a recall, and I'm just going to recall this on the side of our page, if we have some slope of, let's call it a over b, the slope that is perpendicular, and you can draw like a vertical and a horizontal line and a box in the corner. Perpendicular means that they meet at a right angle. Okay, that slope would be, this is called the negative reciprocal. Reciprocal. Okay, so what we do is, number one, we flip the number. So flip the fraction or flip the number. Okay, so instead of writing a over b, we write b over a. Okay, and then step 2 is flip the sign. Okay, so a over b, by the way, a over b is one full number. If this number is positive, then this number here is going to be negative. And usually what we do is we just denote that negative on the integer in the numerator. Okay. One other thing about perpendicular slopes is if we were to multiply perpendicular slopes, so a over b times negative b over a, what would we get? Well, a times negative b is negative ab, and b times a is also ab or ba, doesn't matter, okay? But if you think about it, ab cancels out, it actually equals -1. So slopes that are perpendicular to each other, or negative reciprocals, multiply to -1. So that is another property. So let's take a look at example 5. Determine an equation of a line that is perpendicular to the tangent of the graph of f at x equals 1 over x at x equals 2, and that intersects it at the point of tangency. So I'm going to recall, we just found the derivative of this. So I'm going to recall from the previous question that the point at x equals 2 is 2, 1/2. Okay, and also f prime at x is going to be -1 over x squared. I know in the previous one we did t, but it doesn't matter what the variable is. Okay, it's going to be the same derivative. Here, I'm going to put from example 4. Okay, more from example 4. We already found out f prime at 2. So the slope at that point, 2, 1/2, is -1 over 4. So all three of these pieces of information came from the work that we've already done. So now let's find the slope that is perpendicular. So all of this information is about the tangent line, right? The slope of the tangent line at 2, 1/2. Now, the slope that's going to be perpendicular is obviously the negative reciprocal of -1 over 4. So 1 over 4, when we flip that number, we get 4, or 4 over 1. Okay, and this number is negative, so our number is going to be positive. So the slope that we're looking at now is 4, +4. All right, let's go back to the question and actually figure out what this is asking. So we're going to determine the equation of a line. Okay, so we know that our line is going to be in the form of y equals mx plus b. Okay, that is perpendicular. So we have that. We have the slope of 4. So perpendicular to the tangent of this graph. Well, we already took that, obviously, that information from f at x and from example 4 at x equals 2. So what this is telling us is we're using the same x and y values. So we can sub in x and we can sub in y. And then it says, and that intersects it at the point of tangency. Yep, so it does, because the point of tangency goes through this point here. So the information that we took from the original point of tangency is the point. Okay, it's going to intersect right there. Which, because that point, because we're dealing with a tangent line, it only intersects at this point, and then we're dealing with perpendicular. So we're taking the same slope, but perpendicular, and that's it. So now we can have 1/2 equals 8 plus b. Okay, 1/2, we're going to bring this 8 over, minus 8 equals b. So we get 1/2 minus 8 is going to be 16 over 2. So we get negative 15 over 2 equals b. So our equation is y equals 4x minus 15 over 2. Now, just for an expansion and just to practice, I'm going to go ahead and put this into standard form. Okay? The coefficient of x is positive, so I'm going to leave the x on the right-hand side, and I'm going to bring over the y. So we're going to have 0 equals 4x minus y minus 15 over 2. So 2 things are satisfied already. We have ax plus by plus c. So we're in the correct form. We're all in order. It equals 0. The coefficient of x is positive, so that's good. Now, number 3, we have to multiply this entire equation by 2 in order to get rid of this denominator. So the 2 has to be multiplied by everything, and our equation in standard form is going to be 8x minus 2y minus 15. Okay, so back to decimals. If we do 8x minus 2y minus 15 equals 0. And I have to, this is not going to look perpendicular until I change the grids to the same window, because it's going to look distorted. All right. Well, these are perpendicular. So this green line and this blue line are actually perpendicular. Okay, again, I can't get this graph to be precisely like square. So it's not going to look perpendicular from here, but they are. Okay, we know that from -1/4 and this being a slope, and then the 4 being the slope. Okay, they both intersect at 2,5. So what these mean is that the blue line is the tangent line, and the green line is the normal to the tangent. Okay, and again, they go through the same point. Okay, the existence of derivatives. A function f is said to be differentiable at a if the derivative, so f prime at a, exists. Well, yeah, that makes sense. If the derivative exists, it's differentiable. Okay, at points where f is not differentiable, we say that the derivative does not exist. Okay, so this is our wording. It's not as though it's not defined. It specifically does not exist, and we can say that. Okay, that's the wording. 3 common ways for a derivative to fail to exist are shown. So if there's something called a cusp, right? So it comes down and then it launches back up. This cusp, the derivative does not exist. okay? A vertical tangent, so we see this often. So a vertical tangent is when we're taking a look at like a point of inflection, so we go from like concave up, right? This is like a concave up to a concave down. That point of inflection right there, there's a vertical tangent. I'm going to put POI, point of inflection. Okay, and then if there's a discontinuity. So in this case, there's a jump. So if there's a discontinuity, this could even be like an endpoint. Okay, also endpoint, because essentially what happens is this is an endpoint of this part of this piecewise function, and then this right here is an endpoint of this part of the piecewise function, and still, because of that discontinuity, the derivative does not exist. So please note, it is possible for a function to be continuous at a point, and we can see that here in this cusp, okay? Or even in this point of inflection. These functions are continuous, yet not differentiable at that same point. However, if a function is not differentiable, then it is also, sorry, if a function is differentiable, then it is also continuous. So this goes one way, but doesn't go the other. All right, example 6. Show that for the absolute value function, f at x equals absolute value of x, is not differentiable at x equals 0. So as a recall of the absolute value, so these two bars here beside x mean absolute value. And if you can recall the graph of an absolute value function, okay, it is two lines that are always positive. Okay, so it is a piecewise function. Okay, so this part of the line, so f at x equals absolute value of x, it is a piecewise function where from 0 and greater than 0, f at x is going to be x, and on negative infinity to 0, so anything less than 0, we're actually dealing with negative x. And what that negative x does is it turns all of these negative numbers into positive. So no matter what, it's the line that should have been down here gets reflected up, right? Because that negative sign in front of the x, or in front of the function, is a reflection of the x-axis. So all the absolute value function does is ensure that everything stays positive in the original, not after transformations, but definitely in the original. So if you think about this, the slope from 0 to infinity is going to be 1, right? Because these are lines. These are in the form y equals mx plus b. B being the y-intercept of 0. So these two are in the form y equals mx. So the slope of 1 and the slope of negative 1 are right here. Okay, so if we're taking a look at the derivative of f prime, so f prime at 0, we're going to take a look at the limit as h approaches 0, but we're actually going to sub in this time, okay? So 0 plus h minus f at 0 all over h. So if you think about what's going on here, we're taking a look at 0 plus h is just going to be f at h minus f at 0. Well, this point here is the origin, 0, 0, so that's just 0. And that's going to be all over h. Okay, so the limit as h approaches 0, so f at h over h. So if you're thinking of f at h, this is kind of like the original, right? Like if you're thinking about like f at x, where that's the absolute value of x. Well, f at h is going to be just the absolute value of h, and that's going to be over h. Okay? And because of this graph and because of the piecewise function, we know that the graph has, we want to call it a corner at that origin, 0, 0. So what we're going to do is we're going to, okay, so consider one-sided limits. There we go. Okay, so we're going to consider the limit approaching 0 from the left, and then we're going to consider the limit approaching 0 from the right. Okay, so if we have the absolute value of h equals h, okay, this occurs when h is greater than 0, right? Because the absolute value is just changing whatever h that we have to a positive h. Okay, and then whereas the absolute value of h is going to equal negative h, okay, when h is less than 0. Let's go greater than or equal to 0. I always just group in the equal to with the positive. Okay, so the limit as h approaches 0 from the negative side of the absolute value of h over h, right? We're just taking that from the limit, is going to equal the limit as h approaches 0 from the negative side. So because we're approaching from the negative side, this is going to have negative h subbed in. Okay? And if we cancel these out, we get the limit overall as h approaches 0 from the negative side of negative 1, which is a constant. Well, we know the limit of a constant is just that constant. It's going to be negative 1. Okay, and then the limit as h approaches 0 from the positive side, okay, that means we're going in from the positive side. It's going to be, the original function is the absolute value of h over h. Is going to be the limit as h approaches 0 from the positive side. So because we're going in from the positive side, this is just going to be h over h, which obviously just cancels to 1. And we get the limit as h approaches 0 from the positive side of the constant 1 is again going to be a constant. So if we assess the limit as h approaches 0 from both the left and the right, okay, and by the way, this, like, I use this graph, but this graph is actually x. So when we're saying h, we're using like the gap between 0 and h, okay? So it's a little bit different. So it is not based on this graph. It's just based on the h value. So the left side limit does not equal the right side limit, okay? And therefore, the limit does not exist. Okay, so please note other notations for derivatives. So if the question gives us an equation in the form f at x, what we want to do is we want to use f prime at x. We have to make sure that these notations that we're using align. Now, if we're given y, we can use y prime, but what we usually use is dy by dx, which is Leibniz notation. Okay, it's read dy by dx, right? By would be like that division symbol or the fraction symbol. Okay, so dy by dx. Yeah, and all this means is the derivative of y with respect to x. Derivative of y with respect to x. Okay, and that just means that we have some y equation with an x over here. So it could be x cubed, x squared, I don't know, 1 over x, whatever it is, we have some y equation with respect to x, and dy by dx is just the derivative of that.